Hello dear students, I welcomes you to lecture 11 of Topology of Matrix Spaces, Unit 1st Matrix Spaces. Hello dear students, I welcomes you to lecture 11 of Topology of Matrix Spaces, Unit 1st Matrix Spaces. In today's lecture, we study definition of open sets of matrix space and solve some problems on open sets of matrix space. So start lecture with definition of matrix, open set of matrix space. Open set of matrix space. Let HD be a matrix space let capital G is subset of X is said to be an open set if for every small p belong to G, there exist a positive real number small r greater than 0 such that open ball about P with radius r is contained in G. This is the definition of open set. HD be a matrix space and G is subset of X is said to be an open set if for every P belong to G there exists a positive number r greater than 0 such that open ball about this point P with radius r is again contained in G. So this is a set X, and G is containing Suppose this is set G. Okay, this is X, this is set G. If P is any point, P is, suppose this is point P, then there exists a number R which is greater than 0 such that open ball, when you draw open ball about this point P, then this open ball is contained in set G. Suppose this is point P and this is radius R, then this is contained in set G, then this G is said to be open set in X. Okay, this is the definition of open set. Note, empty set phi and set X itself is an open sets. Empty set phi and set X itself are open sets in X. In X itself is an open sets in X. Okay, this is the definition of open set of matrix space. Example 3. Let X is equal to R2 and D is equal to equivalent metric let G is equal to set of order pair x1 x2 such that belong to R2, this x1 x2 in R2 such that 3x plus 4y greater than minus 12 Then prove that G is open set in X solution geometrically we can sketch the region representing G first we sketch the straight line 3x1 plus 4x2 is equal to minus 12. When x1 is equal to 0, 4x2 is equal to minus 12 implies that x2 is equal to minus 3. When x2 is equal to 0, 3x1 is equal to minus 12. This implies that x1 is equal to minus 4. We draw a figure. Okay. Okay, there is a point. This is origin 1, 2, 3, 4, -1, -2, -3, -4, 1, 2, 3, 4, up to so on. This is x1 axis, this is x2 axis. Okay, and this side -1, -2, -3 and -4. First point is, our point is 0, -3. 0, -3. We get a point at this location. Next point is -4, 0, 0, -4. Therefore, this is this is the equation of line 3x1 plus 4x2 is equal to -12. Okay, this is minus point -4. Okay, suppose this is -4. Then our region is this is a line 3x1 plus 4x2 is equal to -12. Our region is above the line. The equation is 3x1 plus 4x2 is greater than -12. Therefore, our region is above this line. Therefore, our working region is this side. This is our working region. Suppose in this side, this is a point P1, P2. Then we draw an open ball about this, and we see that we show that this point is contained in this set G. This is a point P1 and P2, and this is the radius R. Okay. Then we have to show that this open ball contained in G using the above procedure. let P1 P2 belong to G be any point the perpendicular distance from point P1 P2 to the line 3x1 plus 4x2 is equal to minus 12 is equal to modulus of 3p1 plus 4p2 plus 12 divided by root 3 square plus 4 square. Since this is the formula, since perpendicular distance from point A0 B0 to line ax plus by plus c is equal to 0 is obtained by the formula root a0 a0 plus b0 plus c divided by root a square plus b square. Okay, using this formula we get this 3p1 plus 4p2 plus 12 divided by root 3 square plus a square. Here a is equal to 3, b is equal to 4 and c is equal to 12. This is equal to 3p1 plus 4p2 plus 12 divided by 5. Take r is equal to 3p1 plus 4p2 plus 12 divided by 7. Since this is less than the point 3p1 plus 4p2 plus 12 divided by 5. Note that the denominator of r is obtained by adding the coefficient of numerator three plus 4 is equal to 7. 1 upon a plus b is less than 1 upon root a square plus b square. This is the property. We will prove that open ball about point P1, P2 with radius R is contained in G. We prove that this open ball about point P1, P2 with radius R is contained in G, or our upper region. For this, we assume that point Y belong to Y1, Y2 belong to open ball about P1, P2 with radius R. Let Y1, Y2 belong to open ball about point P1, P2 with radius R. This implies that since D is an equilibrium matrix, then distance between point Y1, Y2 and point P1, P2 is less than this R, since D is equilibrium metric. This implies that by definition of equilibrium matrix, this is equal to under root y1 minus p1 bracket square plus in bracket y2 minus p2 bracket square less than R. This implies that modulus of y1 minus p1 is equal to this, or consider this is equal to root of modulus y1 minus p1 bracket square. This modulus of y1 minus p1 is written as square root of modulus of y1 minus p1 bracket square is equal to, this is also written as, this is equal to modulus of y1 minus p1 bracket square plus modulus of y2 minus p2 bracket square. This is less than R. This implies that minus R less than y1 minus p1 is less than R, and this implies y1 is greater than p1 minus R. Similarly, we show that y2 is greater than p2 minus R. Therefore, 3x1 plus 4x2 is greater than, consider not x1 y1 consider y1 x2. Therefore 3y1 plus 4y2, because we take point y1 y2, therefore we consider the line 3y1 plus 4y2. This is greater than 3 into value of y1 is p1 minus r plus 4 into value of y2 is p2 minus r is greater than 3p1 plus 4p2 minus 7r. Okay, 3p1 minus 3r plus 4p2 minus 4r. 3r plus 4r is 7r minus 7r is greater than 3p1 plus 4p2 minus 7 into value of r is, we take value of r is 3p1 plus 4p2 plus 12 divided by 7, and this is greater than 7 cancel, we get 3p1 plus 4p2 minus 3p1 minus 4p2 minus 12. Therefore 3y1 plus 4y2 is greater than minus 12. Therefore this point y1 y2 lies in the upper half of the line 3x1 plus 4x2 greater than minus 12. This implies that point y1 y2 belong to G, and this implies that open ball about point P1 P2 with radius R is containing G, and hence G is open set. Hence G is open. This is the solution of this problem. Now we take next problem. Example 4. Let x is equal to R2. And D is equivalent metric. Let G is equal to set of order pair x1, x2 belong to R2 such that minus 12 is less than 3x1 minus 2x2 less than 6. This is the set G. Then show that G is open in R2. We have to show that the point contained in this set is and take open ball about that point is belong to set G. Then our set G is open set. Solution. First we draw the we draw a figure. Okay. Consider a straight line three x1 minus 2x2 is equal to 6. X1 equal to 0 implies that x2 is equal to minus 3. Therefore we get point 0 minus 3. x2 is equal to 0. This implies that x1 is equal to 2. Therefore we get point 2 0. Consider a straight line three x1 minus 2x2 is equal to minus 12. x1 equal to 0. This implies that minus 2x2 is equal to minus 12 is x2 is equal to 6 plus 6. Therefore we get point 0 6. x2 is equal to 0. This implies that 3x1 is equal to minus 12. This implies that x1 is equal to minus 4. Therefore we get point minus 4 0. We draw this straight line point 1 2 3 4 5 1 0 1 2 3 4 5 6 -1, -2, -3, -4, -5, 6. This is x2 axis. This is x1. The point -1, -2, -3, -4, -5. Okay. First we draw the line 3x1 2x2 is equal to 6. So the points are 0, -3. Points are 0, -3. 0, -3. Next point is 2, 0, 2, 0. Sorry, 0. Okay, not this is a point. 0, -3. This is point. 0, -3. And next point is 2, 0. This is the line. Then we draw the line 3x1 2x2 is equal to 12. We get the point 0, 6, 0, 6, 0, 0, 6. This is 0.06. Okay. And then we get next point is -4, 0, -4, 0, -4, 0. Then we draw the line our region is this is line 3x1 -2x2 is equal to -12, and this second line is 3x1 2x2 is equal to 6. Our area is lies between this region, between these two lines. Then our working area is set G is, this is set G. This is our working area for this problem. Okay, this is the figure of set G. Now we have to show that G is opening R2. Let point P1, P2 belong to set G, be any arbitrary point. The perpendicular distance of point A0, B0 to the line ax plus by plus c is equal to 0 is modulus of a0 plus b0 plus c divided by root a square plus b square, root a square plus b square. This is the formula of perpendicular distance of point to the line. Therefore, the perpendicular distance of point P1, P2 from the line three x1 minus 2x2 is equal to minus 12 is modulus of 3p1 minus 2p2 plus 12 divided by root 3 square plus 2 square. Similarly, the perpendicular distance of point P1 P2 from the line three x1 minus 2x2 is equal to 6 is modulus of 3p1 minus 2p2 minus 6 divided by root 3 square plus 2 square. Okay, this is the distance between point P1, P2, the line 3x1 minus 2x2 is equal to minus 12, and the distance between point P1, P2 to the line 3x1 minus 2x2 is equal to 6. is respectively modulus of 3p1 minus 2p2 plus 12 divided by root 13 and modulus of 6 minus 3p1 plus 2p2 divided by root 13. We choose R less than these two values, less than these two values. Note that one upon 5 is less than 1 upon root 13, as 1 upon a plus b is less than 1 upon root a square plus b square. This is the formula for choosing values. Choose R is equal to minimum of 3p1 minus 2p2 plus 12 divided by root 13 and 6 minus 3p1 plus 2p2 divided by root 13 or root 13 is less than 5, then we choose this is replaced by 5. Because we use this, therefore R is equal to minimum of 3p1 minus 2p2 plus 12 divided by 5, 6 minus 3p1 plus 2p2 divided by 5. Okay, we will prove that open ball about point p1 p2 with radius r is contained in G, set G. This is our target. Then we consider the point in this open ball. Let order pair y1 y2 belong to open ball about p1 p2 with radius r. This implies that distance between y1 y2 and point p1 p2 is less than r. Since D is equivalent matrix, since D is Euclidean metric, then we get root root y1 minus p1 bracket square plus y2 minus p2 bracket square is less than this r, since or consider modulus of y1 minus p1, this is equal to, this is written in the form of under root modulus of y1 minus p1 bracket square, this is less than root modulus of y1 minus p1 bracket square plus modulus of y2 minus p2 bracket square, which is less than r. Therefore, modulus of y1 minus p1 is less than r. This implies that minus r is less than y1 minus p1 less than r. This implies that p1 minus r is less than y1 less than p1 plus r. This implies that, or therefore 3p1 minus 3r is less than 3y1 less than 3p1 plus 3r multiplying by 3. This is equation first. Similarly, modulus of y2 minus p2 is less than r, and this implies that, or this implies that minus r less than y2 minus p2 less than r. This implies that p2 plus r less than y2 less than p2 plus r. Here is minus. Multiplying by 2, we get 2p2 minus 2r less than 2y2 less than 2p2 plus 2r. This is equation second. adding 1 and 2 we get 3p1 minus 3r minus 2p2 minus 2r less than 3y1 minus 2y2 less than 3p1 minus 2 3r minus plus 3r minus 2p2 plus 2r. Therefore 3p1 minus 2p2 minus 5r is less than 3y1 minus 2y2 is less than 3p1 minus 2p2 plus 5r. Okay. But r is equal to, we choose r is equal to 3p1 minus 2p2